Alright, so in this problem we have a horizontal spring with a constant of 700 newtons per meter. So let's highlight that because we're going to need that value in a moment. And it's compressed 2 centimeters. So that's what I've drawn here. I have a ball sitting here with the mass labeled. And this would be the equilibrium position. And the spring has been pulled back 2 centimeters or 0.02 meters. Let's see, we placed a ball in front of it, so I've already shown you that with the mass. And then the spring is released. So we've left our initial conditions. So initially we have spring potential energy. The ball is at rest. And we are at a height of not above the ground, so we're on the ground. So we can say y initial is equal to 0 meters. Now we're going to release the ball, and that is going to transfer the spring potential energy into the motion of the ball, or its kinetic energy. So in the final conditions, we know that the ball has traveled a total of 10 centimeters or 0.1 meters. We're staying along the ground as a horizontal track. So our y final is also 0. We're looking for the velocity final, that's what that says here. And the spring has been released, or it's relaxed, which means that it's going to relax to its equilibrium position, and x final is going to equal 0. We also have to note that in this problem we have friction. So we do have a non-conservative force at work. So we do have to take that into account. Alright, so our initial velocity here is 0, and anything times 0 is 0, so we're going to have 0 initial kinetic energy. We are on the ground, so we define the ground as y equals 0, and anything times 0 is 0, so our initial gravitational potential energy is 0. Now the spring is compressed initially, so we get 100, or not 100, 1/2 times 700 newtons per meter, which is the spring constant, times how much the spring is compressed, so 0.02 meters squared. Technically speaking, it should be negative, but we're going to square it anyway, so I never worry about that minus sign. Now we're going to have to subtract off the work non-conservative. This is a frictional force opposing the motion of the object, so that means it's going to be negative. And remember, work is force times displacement, so we have to take the force due to the friction over the distance, or times the distance, I should say, that force is experienced, which in this case is 10 centimeters or 0.1 meters. And that allows us to establish how much energy we have initially in the system minus how much we lost to friction. So that is where we get the 0.065 joules. Now let's look on the final side of the equation. So we're going to take 1/2 times the mass, and the velocity final squared is what we're looking for. So we're going to leave that, and we're going to allow it to carry through the problem. We are still on the ground, so we're going to take y final is 0. So anything times 0 is 0, so we have 0 final gravitational potential energy. And now our spring has relaxed, we've released it, it's gone back to its equilibrium position, so that x final is 0, so we're going to take 1/2 times k times 0 squared, which is 0. So in essence, we've taken our initial spring potential energy, lost some energy due to work non-conservative, and that got turned into kinetic energy. So we can divide by the 0.1 on both sides, and then we can take the square root in order to get that the final velocity is 0.81 meters per second.